Welcome to Year 10 Science in the unit of Chemistry 2. In this unit we are looking at controlling the rates of reaction. This is video 1, and in this video we are looking at energy transfers. So the outcomes for this unit are listed here. You'll also find them in your booklet. In this video we are going to be looking at the first two outcomes. So describe a chemical reaction as either endothermic or exothermic, and understand the connection between activation energy, bonds in reactions, products, and delta H. Okay, so thinking back to our unit on chemical reactions, and we said there were many different types of reactions. You've got a cartoon there showing some. We also learned that we use chemical equations to represent chemical reactions, and we said that a chemical reaction must be balanced and include all of our states of matter for both the reactants and the products. All right, now, when we think of a chemical reaction, okay, there are different indicators of whether a reaction has occurred. So different things you can see, smell, feel, okay. So yeah, a range of factors there that are listed that tell you if a chemical reaction has occurred. And yes, there's a character there that looks very familiar. Okay, now energy transformations and chemical reactions. So what has energy got to do with a chemical reaction? Well, all chemical reactions do involve a transformation of energy. Now, you would have done energy transfers back in year 7 and 8, where you may have chemical energy in a battery that is then transferred to kinetic energy in a toy robot that moves, or chemical in your energy, chemical energy in your food, which you transfer to kinetic energy, so movement energy when you walk, and heat energy through metabolic processes. Now, the energy stored in chemical bonds, so that's chemical energy, can be converted into light energy, kinetic energy, or heat energy, amongst others, okay, amongst other things. But there are some of these chemical transfers that are occurring. All right, so in this unit, we're going to really look at these thermal energy transfers in our reactions, okay? And we're going to learn some new terminology. Now, in a chemical reaction, energy is always used to break bonds in the reactant, released when bonds are formed in the products. So they're used to break the bonds, so energy is taken in to break the bonds, and released when making bonds. All right, so we've got these two words. Now, you saw them in your outcomes. So chemical reactions are categorized as either exothermic or endothermic. If more energy is used to break the bonds than is released when new bonds are formed, the reaction is endothermic. If more energy is released than was, that's a bad sentence. If more energy was released than was used, then it is classed as exothermic. Let's look at this a bit closer. Okay, measuring the temperature in a chemical system is an easy way to tell us if a reaction has taken place. So whether the system has used heat energy or released it, we can see if a reaction has taken place. So if a reaction is exothermic or endothermic, it will cause a change in temperature, so its surroundings. So it will either feel hot or it will feel cold. Exothermic reactions, they release energy into their surroundings, making things heat up, so they would feel hot. Endothermic reactions absorb energy from the surroundings, which makes the temperature of the surrounding decrease, so they would feel cold. Exothermic, heat exits, it feels hot. Endothermic, heat goes in, it feels cold. So an example, when an acid is added to a base, Okay, so neutralization reaction. There is often no visible sign of reaction. However, if a thermometer is used, a temperature increase can be observed, clearly showing that a chemical reaction has taken place. So you can't see that a reaction has taken place during a neutralization reaction. However, you can record the temperature and see that a reaction has occurred. All right, so looking a bit closer now at our exothermic reactions. These reactions give out heat or light, or both. They feel warm or hot. The products have less energy than the reactants because they have transferred energy out of the system as such. What examples of exothermic reactions can you think of? Okay, so exothermic reactions still, so these are the hot ones, they give out heat. The reactants in an exothermic reaction have more energy than the products. Really think about that, because energy is transferred during the reaction, transferred out. So those first reactants had more energy in their bonds than the product, because they then transfer it during the reaction. As the reaction occurs, the excess energy is released to the surroundings. We can show this graphically with an energy profile. Take note of the axis labels. Okay, so on our vertical axis, we've got the amount of energy, and our horizontal axis, we've got progress of the reaction. So as the reaction time extends, the amount of energy has decreased. Now, just a note there, these diagrams are sketches rather than exact plots, so the axes do not have a specific scale or specific units. Alrighty, let's have a look at endothermic reactions. So these take heat in, and you've got an example there of those instant ice packs that you get if you get an injury. They're an endothermic reaction occurring in there. Now, these absorb energy from the surroundings in order to power the chemical reaction. They feel cold. The product, so the final outcome of the reaction, has more energy than the reactants because they've been taking in energy from their surroundings. They are less common than exothermic reactions. Okay, so thinking a bit more on this endothermic reaction front. The reactants in an endothermic reaction have less energy than the final product that's made. So let's have a look at our graph here. So we've got the energy amount on the y-axis, on the vertical axis, and the reaction progress on the horizontal axis. So you start off with your reactants, and you see there's a rise in the energy value to the products. So the products have more energy in the bonds than the reactants did, and they've taken that in from the surroundings. Okay, so here are some good summaries on our exothermic and endothermic reaction. This is a very good point to note down. Okay, here's a little task for you. I want you to decide what each of these might be. A bushfire burns down a forest, exothermic or endothermic. What do you think? Photosynthesis uses energy from the sun. Is photosynthesis an exothermic or endothermic reaction? Aerobic respiration releases energy for the use in cells. Do you reckon aerobic respiration is exothermic or endothermic? Sherbet cools your mouth. Yum. Magnesium burns in oxygen and releases light. Exothermic or endothermic? A chemical cool pack cools sore muscles. And here we go. There are the answers. Okay, a little bit more on energy level diagrams, so those graphs that we looked at. One of the ways to help describe a chemical reaction is using what we call an energy level diagram. So here we've got a couple of graphs. You've got your energy value on the y-axis, direction of reaction on the horizontal axis. So that is the reaction occurring, okay? Now, an energy diagram is a graph that shows the change in energy of the system as the reaction progresses. Remember from earlier, bond breaking requires bond breaking requires energy, and bond making releases energy. So our endothermic reaction at the top. So we start off with the energy of the reactants. We have this rise in energy as it's absorbed, and then some energy is released into the new bonds, and our energy of our product is higher than the energy of our reactants. We've already looked at these. Now, here we've got our energy of a reactant. So this is our exothermic. We have this energy being absorbed to break the bonds. The energy is released as those new bonds are made, and then our products are a lower energy to our initial reactant. So as we move from reactant to product, energy is absorbed to the maximum point on the graph. This is known as activation energy. Now, we're going to look more at activation energy later, but you need a certain amount of energy to make a reaction occur. At this point, everything is unstable and new products form. As the new products are formed, energy is released to the surroundings. Because of this, the energy goes up and down like it's going over a hill when you look at the energy diagram. So what's the difference? Let's have a closer look at these exothermic and endothermic reactions. In an exothermic reaction, the energy absorbed is less than the energy released. So the difference is pushed out into the surroundings. We say transferred to the surroundings as heat or light. In an endothermic reaction, the energy is absorbed to break the bonds in the reactants. Okay, and that's more than is transferred back to the products that are formed. This leaves the surroundings with less energy, so it's cooler. Okay, now a little bit of terminology here. This symbol, delta H. You might see that sometimes. The difference in energy between the reactants and the products is given the symbol delta H. In chemistry and physics, this symbol relates to a change in what we call enthalpy. You will see it annotated on energy level diagrams. This is the amount of heat given out or taken in during a chemical reaction. Okay, so if we look at this exothermic reaction here, our enthalpy, so our delta H is negative. All right, we can see a negative trend on that graph. In our endothermic reaction, our delta H is positive. Okay, you see that positive correlation? There's more energy in the products than the reactants. Thanks for watching our first video. I'll see you in the next one.